All right, so this lesson is on finding the instantaneous rate of change. So on October 14th, 2012, Austrian skydiver Felix Baumgartner broke a world record for high-altitude dive when he ascended 127,850 feet in a helium balloon and then went into free fall, lasting more than 4 minutes. So what I want y'all to do on your own is 1 through 3, just the front of this. You can use a graphing calculator. That's going to be helpful when you're doing number 2 and number 3, or definitely number 3. So anyway, go ahead and pause the video, do that if you haven't already, and then you can hit play. All right, so the vertical distance that he traveled before he deployed his parachute, which will be the free fall vertical distance, we're just going to take the distance he ascended and then how the height he was when he deployed his parachute and subtract those. So that should be 119,430 feet in free fall. All right, to find his average velocity, we are going to take that distance. Now, because he was falling downward, his elevation was changing, so we're going to make that a negative. And then he fell for 260 seconds. So when you divide that, you get about 459.346 feet per second. That's his average velocity. All right, so then we have this equation for his elevation above sea level in feet, 2 seconds after stepping off the balloon. And this is going to work from 0 to 50. So we have it graphed. So if we were going to label the axes, this would be t, this would be f of t, and this should be in seconds, and this should be feet above sea level. Okay, so he definitely was not traveling at a constant velocity because this graph is not linear. All right, and then see what time does it look like Baumgartner is traveling the fastest. So I would say he's traveling fastest at the end of the graph because that is where the slope is the steepest. All right, so now we're going to estimate his velocity exactly 30 seconds after leaving the balloon. So to do that, right now, all we know to do, what we can do, is find the average velocity. So we're going to find the average velocity between 20 and 30 seconds. So I am going, just to help you kind of discover what I want you to discover from this activity, I'm always going to do the 30 last, right, in my formula. So I'm going to find the average, we are going to do f of 20 minus f of 30 over 20 minus 30. All right, now to find the function's value at 20 and 30, I would just use the graphing calculator. So I put it in y equals, and then I just estimated or calculated a value from the graph. Anyway, I got some really big numbers because he's pretty high. Wait. All right, so it looks like we are going to get 8,000 over negative 10, or negative 800 feet per second. All right, now this next question, you might not have really known what to do with it, but it's asking, is this faster or slower than the velocity exactly at 30 seconds? So the velocity exactly at 30 seconds is going to be the slope of the tangent line at 30 seconds. So if I drew a line that was tangent, which means it just scraped it, it's not too bad. Right, I would say that's the slope. Now, what is the negative 800 is the slope of the secant line. Let me change colors. The secant line that is going from 20 to 30. So that would be this line. Right, and then if you look at those, the secant line slope is less steep than the tangent line slope. So this should be slower. So I'm going to word it just a little different. The slope at 30 is steeper. Okay. And then for B, we want to find the average velocity between 30 and 40. So I'm going to do a similar thing. And again, like I said, I'm going to keep 30 second. So we'll do f of 40 minus f of 30 over 40 minus 30. All right, so we get those values from the calculator. All right, and this time we get negative 1,120 feet per second. All right, and then if I'm going to compare that, let me get to a different color. So 40 is here. So we're going to compare the secant line slope with the other one. And now, to me, the pink line looks steeper than the blue line. So this time I would say faster. The slope at 30 is less steep. So we can kind of figure out that the actual velocity, the instantaneous velocity at 30 seconds is going to be in between these two values. Okay, so I'm going to come over here and just write a few things for you guys. And you can write them in the margins, please. All right, so to get 20, we're going to do f of 30 minus 10 minus f of 30 over negative 10. All right. So these two things are the same. I just wrote it slightly different. All right, and then I'm going to go back on the B part and do the same thing. All right, so this time I have f of 30 plus 10 minus f of 30 over 10. All right, so those two are the same as well. All right, so you guys flip on the back, and I want you to do 4 through 6 for me. I'll write the function up here so you don't have to flip around. So pause it and then do those 3, 4 through 6, and then push play. Okay, so I'm going to continue with that same pattern where the average rate of change, or the average velocity, we're going to subtract f of 29 minus f of 30, and then in the bottom it would be 29 minus 30. Okay, so it looks like we're going to get negative 944 feet per second. All right, and then we'll do it again. But the average velocity between 30 and 31, so f of 31 minus f of 30 over 31 minus 30. Oh, sorry, this one should have been negative 1 up there. Okay, so I'm going to go back and I'm going to do my little fraction. All right, so 29, we did f of 30 minus 1 minus f of 30 over negative 1. Okay, and then this one, f of 30 plus 1 minus f of 30 over 1. Okay, so these estimates are definitely better than we did for 3 because the closer the points are together, the more accurate the slope is going to be. We're just going to say smaller intervals. Okay, and then how could we make it even better? So the way to make it better is to make the interval even smaller. Okay, so if you haven't already, I want you to do 7, do 7 and 8 on your own. All right, so we're finding the average velocity between t equals 30 and t equals 30 plus 30 plus h. And we're going to just take it one step at a time. So we are going to find f of 30 plus h. Now we did this in pre-calculus, where we're just going to take 30 plus h and put it in for x. All right, and then when we square a binomial, I like to use a little shortcut where I'm going to square the first thing in the binomial, multiply them together and multiply by 2, and then square the second. Okay, and then I'll distribute that negative 6. Oh, sorry, that should have been 16, not 6. and then finally, I'm just going to combine my like terms. The only like terms we have are the constants. So f of 30 plus h is going to be 113,450. That number sounds familiar. Minus 960h minus 16h squared. All right. Then we're going to find f of 30 plus h minus f of 30. Now we did f of 30 a whole bunch of times. Every time we did this problem, we had an f of 30. So that 113,450 is f of 30. So I will take my f of 30 plus h and subtract f of 30 from it. So that is going to leave us with negative 960h minus 16h squared. All right. Then we want to find that what we just did, f of 30 plus h minus f of 30, and divide that by h. So I'll take what I just got and divide it by h, and that's going to leave us with negative 960 minus 16h. So D asks, what would we have to do to get the velocity at exactly t equals 30? And then we're going to do that. So for it to be what it is exactly, see, h is the distance in between the point and, like here, h was the distance between, we ended up with 1, the distance between 31 and 30. So what we want to do for that h, we want that h to be 0. So we're going to let h go to 0. And the way that we do that is to take the limit. So we're going to find the limit as h approaches 0 of the, we already have it in reduced form. All right, so if I take h and I put 0 in for it, that's just going to leave you with negative 960 feet per second. Okay, so I don't know if you guys remember from pre-calculus that this is called the difference quotient. All right, now I'm going to write it like what we've been doing with the 30, okay? So it's f of, now we're not going to do 30, we're just going to call that x. All right, and then plus h minus f of x over h. All right, so you can see that with that pattern, the green was how far away the points were from each other, that we were finding the average rate of change. All right, and then the x's on all those were 30, but obviously that changes from problem to problem. So what we want to do is to do the limit so that that distance in between the 2 points you're finding the average rate of change goes to 0, and it becomes the actual velocity at that point. So there is no distance in between them. All right, so let's write that down. All right, so only when we take the limit as h approaches 0 do we get the instantaneous velocity, or instantaneous rate of change. all the other ones, we were finding the average rate of change. But when we did this last step, where we took the limit, that changed it to the instantaneous rate of change. Okay, and so the speed of sound is 1,125.3 feet per second, and we want to know, did Baumgartner go supersonic? He might have, but not at 30 seconds. So if we continue to investigate this formula or this equation, I would be willing to bet that at some point between 0 and 50 he did, but not at 30 seconds. All right, so this leads us to some more specific notes and important ideas about instantaneous rate of change that we'll talk about the next day.